Okay, so I asked you to do the questions on page 561. So number 1 says, the stopping potential to prevent a current through a photocell is 3.2 volts. So VO, stopping potential, 3.2 volts. Calculate the kinetic energy, and that will be EK max, in joules of the photoelectrons as they are emitted. So we know VO is equal to EK max over Q. So that means EK max is equal to Q times VO. So EK max is equal to 1.602 times 10 to the minus 19 coulombs times 3.2 volts. So EK max will equal 5.1264 times 10 to the negative 19 joules. And it asks us for it in joules. If it had wanted electron volts, then we would have divided this by 1.602 times 10 to the negative 19 joules per electron volt. But it only wanted it in joules, so we don't have to. Number 2, stopping potential for a photoelectric cell is 5.7 volts. So VO is 5.7 volts. Again, it wants the EK max, but this time it wants it in electron volts. So again, VO is equal to EK max over Q. So again, EK max is equal to Q times VO. But since it wants it in electron and volts, we can make our life easy here. Q, instead of it being 1.602 times 10 to the negative 19, I can just put it in as 1 electron times 5.7 volts, and my answer will be 5.7 electron volts. Now, if you want it, you could put it in as 1.602 times 10 to the negative 19 joules, get the answer in coulombs, get the answer in joules, and then divide by 1.602 times 10 to the negative 19 joules per electron volt, but you're just redoing, like you're just reversing the steps. So if it wants it in electron volts, you could just go 1E here if you have the voltage. Okay? Number 3, the threshold wavelength, that's lambda O, is equal to 310 nanometers, 310 times 10 to the negative 9 meters. Okay, and so the first part wants the frequency. So we know C equals F lambda, so C equals FO lambda O. So FO is going to equal the speed of light divided by the wavelength. So 2.9979 times 10 to the 8th meters per second divided by 310 times 10 to the negative 9 meters. And when you do this, you should get a frequency of 9.6706 times 10 to the 14th, 1 over seconds, which is a hertz. Okay, that's part A. Part B wants the work function. Okay, so what is the work function in electron volts? So WO equals HFO. So WO equals 6.626 times 10 to the negative 34 joules seconds times 9.6706 to the 14th hertz. And so you get a WO of 6.4077 times 10 to the negative 19 joules. Okay, and now we need to change it to electron volts. There was no cool shortcut here. That shortcut that I talked about in number 2 only works with the VO equation. Okay, but so now we want it in electron volts, so we need to divide by 1.602 times 10 to the negative 19 joules per electron volt. And when you do, you get a WO of 3.999856, roughly, electron volts. Okay, that's part B. Part C says, zinc in a photocell is irradiated by ultraviolet light of 420 nanometers. So the light coming in, its radiation, and I said 420, but it's really 240. So that would be times 10 to the negative 9 meters. What is the kinetic energy of the photoelectrons in electron volts? Okay, so the first step is we need to find the frequency of the light coming in. So again, C is equal to F lambda. So F is equal to C over lambda. So 2.9979 times 10 to the 8th meters per second divided by 240 times 10 to the negative 9 meters. And when you do this, you get an F of 1.249125 times 10 to the 15th hertz. So this is the frequency of the light coming in. And it wants to know what is the kinetic energy. So we need to go to our photoelectric effect equation. EK max is equal to HF minus WO. So we found the WO in part B. We've just found the F, so we can get the HF, and then we can get our kinetic energy. Okay, so H 6.626 to the negative 34 joules times our F that we just found, 1.249125 times 10 to the 15th hertz, minus our WO, 3.999856 electron volts. Now you need to be careful here. When you multiply the first term together, you get 8.2767 times 10 to the negative 19 joules, and then minus 3.999856 electron volts. You cannot subtract these two. Look at the units. You need to change this one to electron volts or the second one to joules, but since it asked for the answer in electron volts, change the first one. So divide by 1.602 to the negative 19 joules per electron volt, which you learned in an earlier video was the conversion. And so you get 5.16648 electron volts minus 3.999856 electron volts. And now when you do this math, you should get 1.166 electron volts as the final answer. All right, number 4 says the work function for cesium, WO, is 1.96 electron volts. Find the threshold wavelength. So from WO, we can find FO. So FO is just going to equal WO over H. WO, however, is in electron volts. H is 6.626 times 10 to the negative 34 joules seconds, so you got to change your WO into joules. It's in electron volts. To go from joules to electron volts, you divide. So going from electron volts to joules, you multiply. So 1.602 times 10 to the negative 19 joules per electron volt. Okay, and when you do this, you get an FO of 4.7388 times 10 to the 14th hertz. Once you have that, now you can get the wavelength because C is equal to F lambda, so lambda is equal to C divided by F. So 2.9979 times 10 to the 8th meters per second F, that's really an F, it just looks like an lambda. 4.7388 times 10 to the 14th hertz. And you get a lambda of 6.3263 times 10 to the negative 7 meters. And this, of course, is lambda O because this was FO. Okay, so 4A, here is my lambda O. Okay, what is the kinetic energy in electron volts of photoelectrons ejected? Okay, so now they're saying the wavelength of light is 425 nanometers.